Okay, so where we are, this is where we are. We have now done FPD, and then we've looked at SFD, which is shear force diagram and bending moment diagram. Okay, what this has given us is the shear force and the bending moment in the structure we're analyzing. Okay, from there, so this is something we've already done. This thing is done. Now we'll compute normal and shear stress. Okay, so this is going to give us sigma x, sigma y, tau xy. So this part is coming next. Okay, how to go from Vm to sigma x, sigma y. From there, we go to Morse circle. Okay, Morse circle, which then takes this sigma x, sigma y, and then gives us sigma A, sigma B, sigma C, and perhaps sigma 1, which is greater than sigma 2. So this gives us the principal stresses. This is something we've done, and we sort of did it ahead of time because once we have these stresses, we'll actually be able to put this to use and just compute the Morse circle. And the next part, which is the part about design, design based on different theories. So there are a number of theories which are used in the course. One of them is called maximum shear stress theory. Okay, this is one of the many theories. Now, this one says that when an element fails, it's basically you need to look at the maximum shear stress, which is sigma 1 minus sigma 3 divided by 2. So it says that this stress is the one which determines failure. So you know this stress because now we know how to compute that using Morse circle. And once we know that stress, we can now basically compute the maximum shear stress. And once we know the maximum shear stress, we can use the factor of safety in order to figure out maybe the diameter or the length of the element. So this is where we are actually we'll get to, but this will come a bit later. But this is what we're working out to. This is already done, which is good, and this part is done. Okay, so this is going to fill us with this important gap, which is how do you actually go from Vm to sigma x, sigma y, tau xy, which then will go and feed us, get to this point where we're actually designing something. This will come later. This is where we're going to go next. Okay, so let's see how to compute the normal and shear stress based on V and M. Okay, so first we'll talk about normal stress, then we'll talk about shear stress, and then shear stress could be due to V, but there's another way shear stress can occur. It's due to torque. So think of a pipe which is torqued, there will be a shear stress. So that will come in that order. First sigma, then tau for V and tau for torque. Okay, so let's start with normal stresses in a beam. Okay, so this is if you have a beam. And then you apply a bending moment. Then clearly what will happen is this beam is going to flex and curve upwards. Now it turns out that, just blow this up a little bit. Okay, let's take this and blow it up. If you look at this beam, you will see that there is a part of the beam which is compressed and a part of the beam which is stressed. Compressed, or this is stretched. Right? It's very clear intuitively. There's also a part of the beam which is not elongated nor stressed. So this part is actually uh, shows no elongation. Okay, which means that there's no stress, because stress is proportional to the elongation. And since there's no stress, well, this is also called the neutral axis. Okay, now what we're trying to do here is we're trying to figure out what is the stress in the element when it is subject to a pure bending moment m. Okay, so that's the next part. We'll compute the elongation, use the elongation to compute the strain, and use that strain to compute the stress through the Young's modulus relation. So let's compute the strain. So here I'm going to redraw that image with of the beam element being twisted or flexed. As I said, there's a neutral axis. Okay. Now, what happens here is this actually uh, is basically an arc of a circle. So what you can do is you can actually extend this, and then you'll see that it actually joins somewhere. That point is, let's call that O, and let's call this angle theta. Okay, this theta is, by the way, non-existent when there's no moment because it's perfectly flat. But the moment you apply a torque, or sorry, a moment, it'll bend. So there is a radius. Let's say that this is R. Okay, now to compare this, I would like to draw the same element when there is no stress at all. So there's no bending moment. Okay, so let's call this length as dx. This is the original configuration. When you apply a moment m, which I'll show here maybe, it bends. Okay, so let's give it a name. Let's call this C D. Remember, I told you that there is one particular axis called neutral axis, which is unchanged. That neutral axis, let me call it CD. So if this is delta x, CD is also delta x because it's unchanged. Clearly, the layers above CD are going to be compressed. The layers below CD are going to be stretched. Okay, so let's just consider one particular section, which is, let's say, below. It doesn't really matter. So let's call that C hyphen D hyphens. So this is C D. C hyphen D hyphen, and that's clearly stretched. Okay, now if you want to write the strain, what's the strain? It's the change in length divided by original length. So if you want to compute the strain in element C prime D prime, it's C prime D prime, that's the length, minus the original length, which is CD, divided by the original length. This is just the definition of strain. Okay. Now I'm going to assume that this distance is y. It will help me in the derivation. Okay, so this is the distance from the neutral axis. Okay. Now we all set. Uh, we can actually write the arc length. CD is the arc length of a circle of radius r. So that arc length is r theta. Right. So r times theta should give me the arc length. For C prime D prime, it's going to be a different radius. It's going to be have a radius of r plus y. So it's going to be r plus y times theta. So because it's further away from the neutral axis, it'll have a different radius. So if you write the strain now based on this C prime D prime, I would have r plus y theta minus r theta divided by r theta. And if you do the math here, I think it comes out to be y divided by r. Okay, so the strain is proportional to the distance from the neutral axis y. We can now compute the stress. It's E times, where E being the Young's modulus times epsilon, it's E times y divided by r. Okay. So let me rewrite these again on a new page. So the formulas are strain is y divided by r, and the stress is EY divided by R. Now, here's a very important thing, and this is a common place where students make a mistake. Sigma is proportional to Y. Okay, what that means is if you take this element and then you draw, let's say, the neutral axis. Okay, so remember that Y is 0 right here. And then here, Y is negative, and downwards y is positive. That's the convention we stick to. And so if you draw the stress as a function of distance y, you'll see the following. You'll see that the top, there's going to be a maximum stress at the topmost surface. It's going to go to 0. There'll be 0 here. Let me just blow this up. This is the cross section. The maximum or compression is going to be here. It's going to be 0 there. And then on the other side, it will again go from 0 all the way to a maximum value. So this part is compression. This part is under tension. Okay. The other important thing, and this is where students typically make a mistake, is that the maximum stress, max negative stress, is at the top. Right? It's this face which is subjected to the maximum compressive stress, and this part has max positive sigma is at the bottom. It's this part which is subject to maximum normal stress. Okay, it's not in the middle, it's on the edges. So what you expect is when things fail in pure bending M, they'll usually fail away from the neutral axis. It will be visible to the eye. because it will be on the top or on the bottom. Okay, there are cases where, in this case, because of the geometry of the material is symmetric, sigma minus the stress in the top most face is the same as the stress in the bottommost face. But for a different geometry, there will be cases where the stress could be higher on the top face and lower on the bottom face. Of course, they'll have the different signs, but it will have a different magnitude too. Okay, and then you'll have to probably look at the one which has the worst possible case, which will be probably be the maximum normal, or the maximum in the sense being positive, or sometimes if you know that the behavior of the material is different in compression and tension, then you'll have to accordingly choose which is the worst one. What after the Y on the left side of the screen? Y on the left side. This is just Y. Y negative and Y positive. Okay, so please remember that the stress is not the same along the cross section. It varies with Y. Okay, that's very common mistake to assume that it is maximum at the middle. It's not. It's actually zero in the middle and actually increases with time. It's increasing with distance. You will actually see that when we do the shear stress, it'll be exactly the opposite. It'll be maximum in the middle and it'll be zero at the edges. And this is a very common place where students make a mistake. They just don't know what is maximum where, and then they get the problem wrong because they don't know how the stress varies as a function of distance. And I'll reiterate this when we talk about the shear stress in a beam. I will see that's exactly the opposite of what it is here. Okay, so with that, we can move on to the next part, which is some interesting things about this formula, the sigma formula. One, we can compute the net force. Okay, what's the force? Force is basically, so I'm going to write dF or delta F is stress times delta A. So this is the stress, or sorry, the force on a small element. If you take the cross section of the beam and you choose a small element here, then this element is delta A. And then I'm trying to compute the force. That's TF. Okay, so that's the force to do a small element. But what I'm really interested in is the total force. For that, I need to integrate delta F over the entire area. So it'll be integral sigma delta A over the area. But sigma is, we have the formula EY divided by R. EY divided by R times delta A. So we can actually pluck out E and R, those are constants, and we're left with Y delta A. Okay, now here's the thing. There's no force in the X direction or in the horizontal direction because this beam is subject to a pure bending moment. So there's no real force. F is zero because there is no force or external force on the beam. The only force we have, and it's causing it to bend, is the bending moment M, but that M doesn't lead to a force F in this direction I've shown. So this is saying that this integral y dA is zero. Okay, when integral y dA is zero, there's something specific, well, something interesting about this formula, which is, you've probably seen this formula. If you have seen the formula for centroid, the centroid formula is integral y delta a divided by integral dA. So this is saying that integral y dA is 0. Okay, so what this means is that the neutral axis is actually the centroid of the beam. Just copy this and make that note. Okay, so let me write that down because that's important. We'll use that fact in order to compute the neutral axis. This implies that the neutral axis is the centroid of the uh, beam. Okay, so if you want to compute the centroid, well, for some geometries we know it. For example, if you have a rectangle, okay, so there is a certain height, call that h. It's clear to us that the centroid is right in the middle. So this is in the middle. So the neutral axis is right in the middle. There's no, it's symmetric, right? But for something like, let's say, a T section, now it's not clear where the centroid is. It's not, you can't just look at it and say the centroid is somewhere. Well, you could say where it could perhaps be. Maybe it's here. But to find the exact location, you would need to use the YDA formula. This is where the centroid is. And then the way to find it is integral y delta A divided by delta A. So we need to do this computation in order to compute the neutral axis. Compute the centroid in order to locate neutral axis. So one thing we'll have to do, if you are given a cross section which is not uniform like a rectangular one, you'll have to first compute the centroid. Without the centroid, you cannot compute the neutral axis and you cannot do any of the calculations. So that will be one thing we need to do before we go ahead and solve a problem. Net moment. Here we'll compute the moment about the neutral axis. So again, going back to this beam, we see that the beam was stretched. There was a axis which remains unstretched, the neutral axis. Okay, now we've seen that there is in fact a stress sigma, and let's say that this area is TA. Okay, so the equation for the moment which by the way is known, is integral force, or in this case, let's put TF times y, where y is the distance from the neutral axis. this is the same direction as delta F, and then the distance between the neutral axis, and that is y. But what's the equation for delta F? The force is stress times the cross-sectional area times y. But then I know that sigma is the formula we derived, E divided by the radius times the distance from the neutral axis. So we'll sub that in here. So we have E divided by R y delta A y. So we substituted this formula. Okay, let's pull E divided by R out. And so we're left with y square delta A. And y square delta A is a well-known equation. It's basically the moment of inertia. So let's denote that by capital I, and we have m equals E divided by R times I. Okay. Also, we have, for example, here written down sigma equals E times R y. So we can combine these two expressions as m divided by I is E divided by R is the same as sigma divided by y. So this is a formula you want to remember because it will be used again and again. Sometimes they'll give you a section modulus. This term here is the section modulus. So if you're given that, it's simply I divided by y.